Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and I work at the Space Telescope Science Institute. And this week, we've got a really great hangout planned for you. As we usually do, this week we are taking a look at some of the, as many times, Hubble has been identified as using and looking at far away, distant objects. But this week, we're highlighting some objects where we inside the solar system, a little bit closer to home. And this week, today, in fact, we have released some new images, new observations of Hubble's looking at Jupiter. And we have with us members of the Hubble Heritage Team, as well as some astronomers who have also helped with these observations. But before I get started, I have a couple of announcements I want to make. This week on Monday, if you go to spacetelescope.org, there is a video contest that just opened up called Ode to Hubble. And if you would like to celebrate Hubble's 25th anniversary, you are invited to make a video and submit it on YouTube, and then enter that into the contest itself. The link is on the web. I put it on the event page here. It's on the event, as well as the description of the YouTube video that we're broadcasting on. So we hope you will join. There are two categories: if you are under 25. And if you are over 25. Now, if you're under 25, that means that you don't know a world without the Hubble Space Telescope, and we're affectionately calling you the Hubble generation. For those of you over 25 years old, there's a separate category. And the prize is actually...
And it comes with a Geritol backpack.
That's right, it comes with Geritol. But the prize is really cool. They are offering a piece of the solar array that actually was part of Hubble early on in its mission, and as well as a plaque and a variety of other things. So please check out the link below in the description, and we hope to see your video soon. Now, if you have any questions or issues like that, just by all means let us know, and we will help you and as much as we can in getting those videos submitted. So we look forward to seeing what you've got this week. So let's get to this hangout. This week we are talking about Hubble has observed Jupiter, and we've gotten some really great observations. In fact, there's a very somewhat rare conjunction that happens every few. I guess it happens every few decades or something like that. It was very rare event that we got here. And with us is the members of the Hubble Heritage Team, and we invite your questions and comments. Also, if you want to interact with us, we have you can comment on the Hubble Hangout event that we're on G+. You can also tweet using the Hubble Hangout hashtag, as well as using the Q&A app. That's actually the best way to interact, because I'm monitoring that, and you can also leave comments on the YouTube page that we're broadcasting from. So, with joining me, as she always does, is Dr. Carol Christian. She's the HST outreach scientist, as well as the driver of the internet, Scott Lewis, at Scientific Scott. Hi, Scott.
How's it going, Tony?
Really good, thanks. And thank you guys for joining me. And so today's panel, we have Zsolt Levé. He's the guy who I think is one of the persons most prominent in the Hubble Heritage Team. Hi, Zsolt. We also have Dr. Mike Wang. He's an astronomer at the University of California, Berkeley. Hi, Mike. And Susanna Duestra. She's an astronomer at the Institute. She's joining us also. Welcome, everybody.
Hello.
And okay. And Zsolt, let me start with you. What have we got here? We've got some images and observations of Jupiter. So why don't you describe a little bit what we've got here?
Okay. So we were able to get one orbit with Hubble. We were privileged enough to get one orbit to look at a fairly rare event, the crossing of several moons across the face of Jupiter, several of Jupiter's moons across the face of Jupiter. If I could start by opening my screen, I can show you these images. And what we have here is two images of Jupiter. Can you all see that?
Yep,
yes.
You see it just fine.
So there are two images of Jupiter taken at different times, about roughly 40 minutes apart. So on the left, we see the disk of Jupiter with those bands of clouds, dark and light clouds. and then we see a number of dots on top of it. On the left, we see a kind of brown, on the left-hand panel, on the lower left, we see a brownish image, and that's the moon Callisto. And to the lower right of that is a black dot right on the edge of Jupiter, and that's a shadow of another moon, Europa, which we don't actually see in that image. Up towards the upper right, we see a yellowish moon, and that's Io, a very interesting moon of Jupiter. And to its upper right, we see its shadow, fairly sharp and distinct shadow. And just below Io, we see another shadow, and that's actually the shadow of Callisto, which is way off to the lower left. So the Callisto's shadow is much farther away from Callisto than Io's shadow is away from it, and that's because Io is much closer to Jupiter. Also, you may notice that Callisto's shadow is much fuzzier, it's much less distinct, and that's also because Callisto is much farther from the planet than Io is. On the right, we have the same, basically the same view of Jupiter, but everything's moved. So the moons have all shifted because they're orbiting around Jupiter at a rather rapid clip. And so Io is now off, almost off the disk on the right-hand, upper right-hand side. And Europa, now we can see Europa itself just inside the edge at the lower left, and Europa's shadow is off to its upper right. And we still see Callisto moved over and Callisto's shadow. So those are basically the two images.
Now you also have an animation of this, I believe, as well, don't you?
Yeah, let me...
Scott, maybe Scott can pull
Scott can show the animation.
Yeah, I'll pull it up here.
All right. So these, so Mike, were you involved in planning these ops? Oh, Scott's got it up now. Here we go. Okay. Yeah. So here is an animation. Why don't you describe this real quick for us, Sol?
Okay. Well, we see individual frames we took during this observation with Hubble, and we simply see the moons marching across the planet as they orbit around Jupiter. Now, this is a loop, so you see it. We have 24 individual frames, so there's about a minute and a half between each frame. So we simply see Jupiter itself rotating, and if you look very closely, you can see that the different bands of clouds on Jupiter rotate at different speeds. So the clouds themselves are shifting across Jupiter, and then above that we see the moons moving across the face of Jupiter, the moons and their shadows.
So this is okay. So this is the animation of the observations themselves. Mike, let me get you in here just a little bit. This particular set of observations shows a pretty unique configuration of the moons of Jupiter and Jupiter itself. Would you describe a little bit? Were you involved in the planning of these observations at all, or did you? Was this on purpose?
What
getting this conjunction?
Oh yeah. We well, we were alerted that the configuration was coming up, and so we looked at when we could actually observe this, and a couple of neat techniques were used. But well, we were actually pretty lucky because Hubble has a 96-minute orbit around the Earth, and so half the time it can't actually point at Jupiter. Jupiter will be on the other side of the Earth from Hubble. So we were lucky that Hubble was on the right side of the planet Earth at the time that these shadows and moons were transiting.
So yeah. Scott, we have a diagram, I think, of the actual geometry of the conjunction itself. Can you pull that up real quick? I want to ask Mike a question about the frequency at which these things, this particular configuration is actually pretty rare, correct?
Yeah, it's pretty rare, and we actually did get a last year. There's great red spot with Hubble.
Right. And we did a hangout. I believe we did a hangout on that as well. So here's the configuration of the geometry of the alignment of these moons, and give us some idea of just how often this happens.
I didn't actually look at the math of how rare this is, but the things that have to be in place for this to be observed is that the tilt of Jupiter's rotational plane, which is where the moons are traveling, has to be aligned such that the sun is shining, well, the sun is lying in that plane. And so it's a similar thing with eclipses on the Earth. There's 2 times a year for the Earth to go into eclipse season. So we can see lunar eclipses or solar eclipses only twice a year during eclipse season. That doesn't mean there's always going to be an eclipse, but the configuration has to be right for that.
Right. Okay.
So same thing with Jupiter. Twice a Jupiter year, you'll have shadows going across the disk like this. But for all 3 of these, for 3 moons to be on the disk at one time is super rare.
Right.
So it's occurred about twice in the last 15 years, and the next one will be 2032.
Nice. So it's a pretty awesome and pretty rare event to see this the way that we have it here, and it's also great that Hubble, like you said, Mike, was in a position where it could actually capture these things. So this is something that I want to come back a little bit to the images and the processing in just a second, but this is something that we're releasing called it's called Hubble Heritage, and these are observations that Hubble makes that's slightly different from normal Hubble programming time, correct? Can you give us a sense of what a Hubble Heritage image is? What is that program?
Well, Hubble Heritage is a program to emphasize the aesthetics, the visual appeal of the images, not so much the science. I mean, all the images, all the data have science. They're science data, so they have science. They're important for science. But we felt that that there are images which have aesthetic value above and beyond their scientific value. So Hubble Heritage hopes to find the best images from Hubble and distribute them as aesthetic images in addition to their science content. So along with that, we have been fortunate to have gotten a little bit of time on the telescope, thanks to the various directors of the Space Telescope Science Institute, have seen it important enough to, first of all, augment some of the observations that already exist for Hubble, and with a little bit of more observing, we could produce an image that would be better than what was possible from the data already existing in the archive. And then in some cases, we're able to propose to do images which have not been done before. And then there are special events, like this Jupiter event, which is kind of a special event that its scientific value is relatively minimal compared to some other kinds of observations that you could do, but it might be of interest to many, many people. And so we were, again, fortunate enough to have one orbit available on the telescope to make these observations. And so this is a group of people here at the Institute, and we propose these observations, we plan them and make the observations, and then do the imaging from them and all the derived products. So,
and I was also going to comment as far as the events. I mean, when we talk about these among ourselves in the group, we will say, well, is this one of these things where one would say, it would be a shame if Hubble didn't, observe that, or people would be interested in knowing what Hubble sees in this circumstance. So there have been other circumstances like solar system objects, like comets, and this one, for example, where amateurs, do a lot of photography because they have much more time than we do. We have only, this one orbit, but it's good to have that and compare, and you can really see a lot more detail in the Hubble observations, but it also has a lot of synergy with the amateurs, and I'm hoping that the professionals will also find this data useful in the overall look at Jupiter as a planet and how the clouds work and all that kind of stuff. So as far as all Hubble observations of Jupiter, it probably has long-term value in that sense.
No, I'm glad you brought that up, the amateur aspect of this, because I've spent a lot of years looking at Jupiter, also through a telescope, and of course it's a very beautiful thing to look at through binoculars and stuff like that. But Susanna, I wonder if I could get you to maybe you have is this something that perhaps amateurs could look at through a telescope? In fact, you also have a component where you're involved with the Galileo scope, right? Would this kind of thing be visible through that?
Yes. So
Okay.
I have right. So you could use a small telescope that's capable of looking at Jupiter, and then you would see the moons crossing the face.
Right, and you can even see these through, you can see the four Galilean moons, especially
Right.
the largest moons, in binoculars or small telescopes, things like that. But these transits, these shadows across, you can also see through a small, I don't know, maybe a 4-inch or a little bit higher telescope, because you need to be able to see the bands of Jupiter and something that would let you get a little more resolving power out of it.
Right.
So I think something like 4 inches might let you see the transits or the shadows. But hold up your Galileo scope real quick. Let's take a look. So this is something that is well, describe it. What are you holding up there?
Okay, so what I'm holding up here is a better version of Galileo's telescope. And originally, 5 years ago, for the International Year of Astronomy, people got together and wanted to have a telescope that was high optical quality but yet inexpensive. And the result was this, I'm not sure if you can see it, is this telescope. It's black plastic. It's not very large. It's about a couple of inches diameter.
Right.
Sort of similar in size to the one that Galileo used 400 odd years ago. And the whole idea was so that it would, the intention was to have the optics be such that you could observe Jupiter's moons as well as Saturn and Saturn's rings. So it's definitely a solar system type telescope.
Okay.
There are other telescopes that you can use as well. This one is just one that I'm familiar with.
Okay.
But that one is it's kind of like a replica of the one that Galileo used when he discovered these satellites in the first place.
Right, except the optics are way better.
It's pretty similar. I mean, the number of lenses and the configuration is very similar to the.
It's
the
very
one
similar. So you have aspherical lenses and so forth in here. But I can tell you that this particular telescope is achromatic.
Well, you got to describe what that is. What is achromatic?
That means that you don't see, if you have like a cheap optics, cheap telescopes, you can see the colors separate.
Right.
Which means different band passes or different colors of light are focusing in different locations. An achromatic telescope of this size is ideal for looking at solar system objects because you see the colors as they really are. You don't see that separation.
Right. So if like Susanna said, if you look at inexpensive telescopes and you look at a bright spot of light, you'll see little prisms or little spreading out of light and of the imperfections in the optics, causing it to basically act like a prism. So this corrects for that. And can you still get this telescope?
Yes, you can.
Okay. So you do a search for Galileo scope, and you'll be able to get that, and you can see these kinds of things that we're talking about here. But Hubble is not a Galileo scope. It's a little bit better, a little bit of a step up.
Before we transition to that, with some amateur astronomers that I know, they actually, one of them, Stuart Foreman, who's up in the Bay Area here in California, did go out and observe with his telescope, and he posted up his frames with the help of Mike Phillips, who's an amateur astronomer in North Carolina. And here is, this is up on YouTube, so I'll share it out as well. But this is what he was able to see from the Bay Area.
Right.
And this is his frames going back and forth.
Yeah, it's really cool that the Hubble Heritage program decided to look at this the system of transits, because these were observed by Cassini, and historically they were some of the first solar system observations with a telescope. And NASA likes to commemorate these contributors to astronomy by naming missions after them. So Galileo was the name used for the mission to the Jupiter system, Cassini, the mission to the Saturn system that's still going around there, and Hubble was also named after a famous astronomer who made fundamental contributions to science. So it's really cool that, I mean, Cassini was the first to observe shadows of moons going across the disk of Jupiter, and they led to the first precise determination of the longitude difference between Paris and Copenhagen, for example. So a lot of good science was done based on these types of observations, and now Hubble has captured images of it at much higher fidelity than those astronomers ever could have dreamed of.
Yeah, but the
Right.
cool thing is that with your own telescope, you can see what Hubble is seeing. Maybe not with the same resolution, but it's one of the few times when you can actually follow along with Hubble.
That's
Yeah.
right. That's a good point.
So
Zolt was-
besides that, I actually, before you go back to Zolt, besides that, I just wanted to understand what, okay, so we got this link to the public and to amateurs. Why should we study Jupiter or any object in the solar system with Hubble? We have satellites that go there.
Well, we don't actually have any missions in orbit around Jupiter right now. The Juno mission is on its way there, and it should arrive next year. But it's not going to do the same type of things that Hubble can do. So Hubble's main advantage, well, it has two main advantages for studying Jupiter. One is that it can sense in the ultraviolet. So we can't do that from the ground because the Earth's atmosphere blocks ultraviolet. Good thing, because we would die otherwise. But the other advantage is that Hubble can take very sharp images at optical wavelengths, so we can track motions of these clouds as they move, and you can even see that in the animation just over this one Hubble orbit. So the animation on the Hubble site shows just maybe 50 minutes of these moons moving across Jupiter's face, but you can also see the clouds as they rotate. Well, as Jupiter rotates, you can see the clouds moving, and they move at different speeds. So some of the belts have different jet speeds than other belts, and by charting those motions, you can see what the weather is on Jupiter, and we can understand the physics of atmospheres, make parallels to the Earth's atmosphere. In fact, parallels to the oceans of Earth. Some of the vortices, like the Great Red Spot, are types of vortices that are present in the oceans of the Earth. And Jupiter is our closest example of what exoplanets are like. And a lot of current interest is in finding planets around other stars. But it's hard to study those in detail. And by studying Jupiter, we can sort of make analogies to some of the processes there.
Awesome. Thank you. Yeah, I'm glad you brought that up, Carol, because Zolt was saying that, primarily the Hubble Heritage images are chosen for their aesthetic values, but there's good science that can also be done.
But we also had the shrinking red spot this year too, so that was another case where I guess Hubble was useful for helping to monitor that.
That's right.
Yeah.
That's right. So there's a lot of good, useful science that can be done using Hubble, and primarily because, as you point out, Mike, there's not a current mission around Jupiter to make these observations. So Hubble is very valuable in that sense. So I have a question from Charles Bell, and I think I'm going to give this to you, Zolt. It goes, how do you keep the CCD camera pixels from saturating from such a bright object? Hello?
Zolt looks frozen. Well, basically, we
Okay.
have to make sure the exposure is short enough, and then it won't saturate.
Right.
So we have calculators based on the known spectrum of astrophysical objects. We can calculate through any filter on Hubble what's the right exposure time.
That's right. That's Carol, we've never actually talked about this before, have we? The exposure time calculator. There's a tool that astronomers can use to actually figure out what exposures to set for Hubble based on what they're looking at, correct?
Mhm.
Carol?
Yes, I'm here.
Okay.
Yes.
Okay.
Yes, I mean, actually, that would fill a whole hangout, not just the exposure.
I know. Well, that's actually a good idea. We should do one
How
on that.
you figure out how to do these observations. And I think the beautiful thing about this particular observation in calculating the exposure time, and also the beauty of the detector, is that you get enough dynamic range that you can actually see the detail of the shadows, which are very dark. You can see the different brightnesses of the Jupiter bands, and you can also see those moons, which I found. Now, in one case, Callisto, you have to adjust it a little bit to see that Callisto is pretty dark, but still, the fact that you can get the exposure time right, that you get all that stuff at the same time, I think is pretty impressive for you guys who planned the observation. I just was a cheerleader. I had nothing to do with the exposure time.
Right, but that that is something that we should have a hangout specifically on that.
Because it's tricky.
Yeah, it is. But there are tools, as Mike pointed out, that astronomers can use to help figure out the exposure time. So that's how they keep.
Right.
That's how they kept it from saturating such a bright object. It's just a matter of figuring out the exposure time. So I'm seeing a new term on the Q&A app: Hubblers. I've never heard that before. Hubblers.
I kind of like that over Hubble.
Yeah,
I like Hubblers over Hubble huggers. I
don't know. I'm a Hubble hugger, but Sev Dust Bunny goes, "Good evening, Hubblers." And also, we have a question here from Wired Magazine. Hello, Hubblers. Nick Stockton here from Wired Magazine. Was wondering if observations like these contribute. And Mike, I'll direct this to you since I'm not sure where Zolt went. Was wondering if observations like these contribute to science of looking for exomoons that's happening with Kepler and other telescopes looking for exomoons. So how do these observations help us with those sorts of observations?
Not really, but there is kind of a tie-in to another program. Jay Paskov had sent us an email about this earlier that Zolt forwarded. But there was a program to look at Jupiter when Venus transited across the Sun. So Venus's shadow was falling on Jupiter. Now you wouldn't see it. All you would see is the whole disk of Jupiter dimming a little bit. But I don't believe that.
Wait a minute. Whoa, well, hold on.
What?
So Venus was passing in front of the Sun.
As seen from Jupiter.
And it was casting a shadow on Jupiter.
Yeah, but not a resolved shadow. So unlike these images where you see a black dot, all you would theoretically see is Jupiter getting a little bit dimmer. The problem is the signal-to-noise ratio. So in order to actually see that, you have to very precisely measure how bright Jupiter is. But as you can see, as it rotates, spots are coming into view and leaving. So there's a number of other reasons why Jupiter's total brightness is changing. So I don't think they were successful in that effort. Now, when we look at exoplanets, again, a lot of times we're looking at small changes in brightness of the host star as the planet goes in front of the star. So there, again, you need very high signal to noise to detect this very small change in brightness. So a moon around another planet is another level of signal to noise that I'm not really sure about whether that's been done or, but I'm sure at some point it will be. But you have all these other noise terms to worry about, like changing brightness of sunspots and things like that.
Can you tell us what the contrast ratio is?
For
say like between the shadow of Venus and Jupiter, was that like 1 in a million, 1 in 10 million?
That I could calculate it. If you give me 5 minutes.
I can give you 5 minutes.
The size of Venus compared to the size of the Sun, basically, and Venus is very small, so or the area of Venus compared to the area of the Sun.
The surface area,
yeah.
It never ceases to amaze me how precise we can get our photometry these days. I mean, Kepler, as Nick pointed out, is looking for other Earth-sized planets, and it's designed to measure tiny dips in brightness in these stars as planets pass in front. And so the fact that we do this now with things like Venus passing in front of the sun and dimming Jupiter just blows me away. That's amazing. So anyway,
it is amazing. I was just going to comment that Kepler, as amazing as it is barely able to find planets that are the size of the Earth. So to find a moon is really tough.
Yeah, it's really hard. Right? It's
especially if you had, say, you had an Earth-sized moon. I'm not sure it would be a moon. It may be a binary planet at that point. But if you had Jupiter and then an Earth-sized satellite around it, it'd be very hard to tell. You know, in a situation where those two are passing between us and the star, and then sometimes the moon is behind or in front, and the dimming of the light, that would be a level of precision that is beyond Kepler's capability, at least.
Right. So that's a great question, Nick. Thank you very much. So Timothy Rampieri, sorry, Tim, I'm messing your name up. With so many moons, and this maybe could go to Carol or Mike. With so many moons, does this make Jupiter's atmosphere complex? In other words, I guess another way of putting that is, does the moons of Jupiter, within it, there are many more than 4, what effect does that have on Jupiter's atmosphere, if any?
I think Mike has to answer that question.
Okay, Mike, you got any idea?
I have a guess, but he's the expert.
Okay. you got a guess for us, Mike? You're muted.
Mike, you're muted. Unmute your microphone and try again.
Okay,
there you go.
Thank you.
Are.
Yeah, it's a minimal effect. There's 2 ways that the moons could affect the atmosphere. They could either change the radiation or sunlight that would reach Jupiter, or they could transfer material to Jupiter. So these actually, we don't have any images prepared, but Hubble's ultraviolet images show one of the clearest links between the moons and the atmosphere. So when you look at Jupiter in the ultraviolet with Hubble, you can see an auroral oval. And it's a similar thing when you look at the Earth. The northern lights, the southern lights, they form an oval around the magnetic pole. And Jupiter's moons actually have streams of particles that travel through the magnetic field and then hit the planet near the auroral oval. And you can see footprints of the moons and watch them as they go around the planet. So there is a linkage there. And so it doesn't really affect the atmosphere that much, but it's useful that there's this linkage, because it can help you study processes in the magnetosphere where these particles are traveling through space. Interesting thing, though, about that question is Saturn is a different case. So Saturn has these big rings. They're not technically a moon or anything, but they do affect the atmosphere there, because the rings are so big they can shade the atmosphere, and you have seasonal changes. If you could imagine floating around in Saturn's atmosphere, depending on what latitude you're at, you may see the rings blocking the sun and get a lot less sunlight than other areas of the planet. So that does affect the atmosphere of Saturn.
Cool. Now, Jupiter also has a small ring, doesn't it?
Yeah, very faint ring.
Very faint ring, but it's not enough, I guess, to make much of a difference in the atmosphere. So, okay, good question, Timothy. Thank you very much. There was a great question from Charles Bell. It went away. I guess he deleted it, but I want to ask it anyway. And that is there a minimum exposure time for Hubble? And Carol, if you may not know this, I don't know, but
I know.
Is there? Okay, good, Mike. Yes. Is there a minimum time that you can take a minimum exposure time?
There is, and it depends not on the telescope, but on the instrument or the camera.
The camera.
So these observations of the moon transits were taken with the Wide Field Camera 3, or WIPC-3 as we affectionately call it.
Right.
And WIPC-3 has a minimum exposure time of less than half a second. I don't remember precisely. It's 0.3 or 0.4 seconds is the minimum. I think it might be 0.3. But anyways, I mean, since we're talking about these technical things, there's something really cool about this image sequence, and I wish Zolt was still here because I forgot the exact number of frames that were taken.
He
But
just
when you
emailed
look at
me.
that,
He said that it crashed. He'll be back in a moment.
Yeah, it's around 25, something like that.
25
and then there are
frames.
yeah, something like
So when we do our science observations, we like to capture the entire disk of the planet because it's really rare that we get to observe Jupiter with Hubble, and so we want to observe the entire thing. But for this sequence, we had a different priority. We wanted to get as many frames as we could to build up a smooth animation, and so we used we could use like a subarray, only reading out part of the detector. Zold, I'm talking about how we used the...
Hi, Zolt. Welcome back.
Hi, sorry about that.
That's all right.
Okay. So we use subarrays. We only read out part of the detector, and this allowed us to build up a whole bunch of frames without pausing to dump the buffer. But basically, we got a really smooth animation at the cost of cutting off the corners. So if you look at that image, we don't have the entire planet there, but we did that on purpose because we wanted to build up a smooth animation.
So
Okay.
I didn't want to backtrack, but I did find that image that you were talking
brilliant.
about, Mike.
Yeah.
So anyway, there it
so
is.
in this ultraviolet image, to the left, you can see sort of like a bright little comma feature. I'm
Right.
going to guess that that's the IO footprint.
Yeah.
IO is the one
Anyway,
that
just to
contributes
show
the
people,
most.
it is on Hubble site as well, if anybody wants to have that image.
Awesome. Okay,
Good work.
great. Okay, so
Yeah,
we're
I just tweeted it out along with the link, and it's in the event page on Google Plus
Great.
as well with the link.
Thanks, Scott.
No problem.
Alrighty. So here's a question from Wout van der Heide, I think. Seeing 3 moons transiting Jupiter is rare, but has there ever been a quadruple transit? In other words, Io, Callisto, Europa, and Ganymede. Has there ever been one with all 4?
I've heard that's impossible.
Hmm.
But I think the issue is that 3 of the moons are locked in a Laplace resonance, which means that their orbital periods are, Io's orbital period is half the duration of Europa's period, and so on. So I think there's a constraint that if some of the moons are on one side, then the other one has to be on the other side, or something like that.
Okay.
I don't think it's possible.
Oh, that's too
I did want to mention, and maybe Zolt will not be happy I did, but there were more than those 3 moons that actually transited.
Yes, that's right.
And no amateur caught this because it is so little, it's really hard to see, but there are little tiny shadows on the images from...
Really? On the sequence that we captured?
Yeah, right?
Yes, it's very difficult to see
It's
on the
really hard to see.
full glow.
We had to blow the image up on a big screen, and we were all like, "Oh, yeah."
Oh, I see. Yeah, you have Amalthea, Phoebe.
Yeah, those two,
Okay.
Amalthea and Thebe. They're just little tiny dots. And
Wow.
in fact, you can see the shadows too.
Do you have does somebody have that?
Yeah.
I can.
You kind of have to zoom in to see those.
Yes. Well, we have a
Yeah, it's
zoomed
really
in.
difficult.
We have a little video that we made that's zoomed in. That's not actually posted on Hubble site. It is posted on the Hubble Heritage site. If I can, let's see, I can bring that up here. Maybe. Oh,
Sorry.
shoot. I didn't. No, that's okay. No, I was gonna. I was hoping
Because
we'd
Carol,
talk
we know
about
how much
that.
we love being asked questions on the spot.
Yeah.
Oh,
It
yeah,
was
because
pretty
I'm the
cool
one who doesn't
because
like to do that.
we knew that they would be crossing the face because we had charts that showed the configuration as we were planning the observations, but we weren't sure that we would actually see them. And sure enough, when we had to sort of even stretch them a little hard, we had to adjust the contrast and brightness such that you could see these. And then the other thing is that there's actually a little bit of noise and stuff in the images, so it's and they're moving across the clouds, which are very complex. So it's a little hard to tell what if you look at just one frame, it's very difficult to tell what's a little tiny moon and what's a cloud feature and what may be some noise in the detector. But if you look at the frames in succession, if you make the movie and look at them, you can see them marching across the frame. And if I try to find,
I've got it up right now.
Oh, okay,
Yeah.
good.
Yeah, there it is.
And I'll put the link out on Twitter and everything like that. But this is found at the Hubble Heritage site, and I'll make
Kind
that.
of
Share
That's
amazing.
right. Heritage, yeah, and you guys should bookmark that site because there's a lot of cool stuff on there. heritage.stsci.edu. A lot of cool stuff there. So, yeah, I can see it now. Look at that. Boy, that
It's
is
so
fantastic.
awesome.
Yeah,
I know. I was amazed.
that is.
So, Mike,
really-
do you know how big those moons are? I haven't looked that up.
No, I would have to look it up. I'm not really good at memorizing numbers.
They're certainly tiny compared to the Galilean ones. I mean,
They are very small. Yeah,
They're about an arc second
that's.
in diameter.
Oh, okay.
Or no, wait.
Smaller
Wait,
than
no.
that.
We're not talking about the Galilean moons, right?
No.
Right, we're talking about
Yeah.
the little tiny guys.
Amalthea,
Oh, they're less than that. Oh, way less than that.
But you know what? I bet if we had captured these frames when those moons were just starting to cross the disk on the limb of Jupiter, they would have stood out a little bit more. This is something that Cassini actually noticed in their first, the first telescopic observations of the Galilean satellites crossing the disk. Is that you could see them? You could see the moons as they first, through a small telescope, you could see the moons as they first touch Jupiter's edge, but once they get towards the center of the planet, with a small
You don't see
telescope,
them.
you can't really see the moons anymore.
Interesting.
So that was something that these early scientists used to figure out that Jupiter probably has an atmosphere because it's brighter in the middle and dimmer around the edges. So basically just finding the light curve as the brightness changes is a technique that we use for exoplanets too.
Well,
So for inquiring minds, Io is about 3,600 kilometers in diameter, and Amalthea is about 250, so less than 10 times, and
There you
Thebe
go.
is 116. So it's
Wow.
pretty darn little.
Yeah, we're
these are-
seeing little guys out there, little rocks out there.
That's a
Yeah.
real tribute to Hubble to be able to resolve those. Those are really great.
Well, they're not
I
really
was
resolved, but we see
by
them.
this image.
so they're about a tenth to a thousandth the size of
Yeah. It's amazing.
big moons.
Okay.
Yeah, they're so small they're not even round. If you
Right. I was noticing that when I looked at them. They're
They're
like
so small they're not even round.
potatoes or Idaho potatoes.
But those would be basically regular satellites. They're not like captured asteroids or something, are they?
No, because these are very close to the planet. Actually, Amalthea, well, I'm not sure, to be honest. But they're considered regular satellites. They orbit in Jupiter's equatorial plane. Amalthea has a faint ring associated with it too. It's very close to
Really?
the planet.
Wow.
Yeah, but the irregular satellites, they don't have to be in the equatorial, orbiting in Jupiter's equatorial plane. Some of those are just like at any angle in polar orbits, whatever. Very
So
far out.
Amalthea and Thebe are two of the four inner satellites, and they are inside the orbit of Io, Europa, and Ganymede.
And you can even see that from the color composites,
Yeah.
because if you look at how far did Io move, in that image, it's a small amount compared to how far did Amalthea and Thebe move. So things that are closer to the planet are orbiting faster than things farther out. So you can just see from this image which one's the closer one.
Right, and the fact that they are closer actually allows them to make a shadow, whereas if they were further out, forget it.
Yeah.
Right. So now that you're back, Zolt, and we lost you there for a little bit, I want to get to some of the nuts and bolts of the processing of the images. And Charles, I'm going to get started with a question from Charles Bell, who's asking, could you show a preview or raw image of Jupiter before any processing to bring out bands across the disk? I'm curious to know how you get the bands of Jupiter to show so clearly. I don't worry so much about, you probably don't have any raw images handy, but how do you get the bands, and what sort of techniques do you do to bring out some of these details?
Well, I'll have to say that we didn't really do anything special to make the bands appear. They basically appear in the images. And again, if I show my screen, I can show some of these images. I don't have raw images, but I have the individual images that we produced. Well, that's interesting. It's not showing up here. I'm having all kinds of technical difficulties. I'm terribly sorry. I don't know why this is not. Okay, here we go.
So this is making the color composite?
Right, I was hoping to show, although my computer is not cooperating with me. I don't know what's going on with this.
Okay, so
I'm terribly sorry.
That's all right. But the images themselves, as far as the, I think Charles is trying to get to. Apparently he is wondering, are there any ways in which you might be able to maximize the contrast, or maybe get the bands to show up a little bit better?
Well, one thing is we used kind of specialized filters, and these are narrowband filters which isolate a very narrow range of wavelengths or colors out of the visible light spectrum.
And those filters are listed. You can see them right there in that image you're showing.
Filters are listed. Yeah, these are these Hubble filter names. So F39395N, F502N, and F631N, and those are codes for telling us what the wavelength coverage of these filters are. So basically, we have 400 nanometers, 500 nanometers, and 600 nanometers. Basically, in
red, green, and a blue image.
Basically, red, green, and blue, although they're not exactly red, green, and blue. But anyway, and they're what are called narrowband filters, which again sample a very narrow range of colors. And the main reason the narrowband filters are chosen is because they let in less light. And Jupiter being relatively bright, a very bright object, especially for Hubble, for a large telescope, that cuts down on the amount of light, so you can use reasonable exposures. If we were using the broadband filters, we'd have to use exposures that were fractions of a second, which is harder to do with Hubble.
And we would run at the minimum exposure time, which earlier in the discussion.
Right, we just talked about that earlier. So
using those narrowband filters also isolates the colors more sharply of the bands in the atmosphere of Jupiter. So each individual filter will isolate a particular color, and that increases the contrast. So if you're sampling a larger range of colors from the white light, you're going to blur out you're going to be mixing colors from what's in the atmosphere, and so those bands will be less distinct.
So, Charles, I'm not sure what filters you're using, but one thing you can do is maybe see if you can get narrower band filters when you take your images. You might get better results that way. So, that's. We
also produce the images in a way that we can adjust the contrast and brightness, just like you can with any photograph, and we kind of maximize that contrast to show all those details. But we also want to preserve the details in the brightest parts of the image and the faintest parts of the image, the darkest parts of the image. So we basically just adjust the brightness and contrast so it provides the best range of tones within each individual image, and then when we composite those together, we end up with a color image.
Right. So here's an interesting question.
About the processing. One of the things that's really important is removing geometric distortion, though, because the raw Hubble images, when they come down, Jupiter isn't the right shape. It's kind of stretched out, and so we have to run a computer program that unstretches it back to what it would naturally appear.
Right. So now that you brought that up, that's a function of the camera as well as the optical path of Hubble as well, right?
Yeah. That's mainly a telescope. Well, it depends on where. So light is coming in through the telescope and it falls on what we call the focal plane of the telescope. And different instruments are in different places of the focal plane. And where
Right, we've shown that
this camera, where WIFC 3 is, it's tilted a little bit with respect to the focal plane. So that stretches out everything.
Right, and so we have a correction. It's a known correction that has to be done on all images, really, not just ones of Jupiter.
All the images, yep.
Yeah, that are taken with Hubble. So here's a good question from Michael S. on the Q&A app. Are there any Galilean moons large enough or close enough from an observer on the surface of Jupiter, let's pretend we're on Jupiter and looking up, to create a solar eclipse? Now, actually, these shadows, if you happen to be on Jupiter and you're underneath and the shadow passes over you, that's an eclipse, right?
Yep. Right. That's exactly what it looks like from space. So if we were on the Earth and experiencing a solar eclipse, then a satellite would see a similar thing. It would see a dark spot on the Earth from the Earth's moon.
The question, though, is the relative size. If you could stand on Jupiter and you're looking back at the sun, what would be the relative size of the moon and the sun? So from the Earth, it's coincidental that during solar eclipse, the moon exactly covers the disk of the sun, right? That's because the geometry between the distance and the sizes is just such by coincidence that they're the same.
Yeah.
That's right. That's a good. I'm glad you brought that up. We're the only place. This is one of the few places in this. Well, it's the only place I know of in solar in the solar system where our moon exactly matches the apparent size of the sun in the sky and completely blocks it out.
And also the only time, Tony, because in the future, as the moon gets farther from the Earth, we're not going to have total eclipses anymore. We'll just have annular eclipses.
That's right. So good question, Michael. That was nice. Okay, so
we didn't actually answer that, right? If we look at the at the color composite, Io shadow and Callisto shadow. Now, Io shadow is really dark and sharp, which tells me that if you were inside that shadow, you would see a total solar eclipse. But Callisto shadow is really blurry, which tells me that if you were there, you would probably see an annulus of solar brightness around the sun there.
So it would be the sharpness of the shadow means a lot as far as the what's the word I'm looking for? Eclipse is never mind.
the type of
the nature of the eclipse.
Yeah, the nature of the eclipse. Eclipticity is the word I was going for.
Is that a word? I don't think that's a word.
I believe it's.
I just made it up.
Ecliptitude.
Ecliptitude. Okay, ecliptitude. That's even better. All right. So, So Judy, welcome back, Judy. It's good to see you again. She's commenting. Hubblers is okay. Makes the transition to JWST easier. We can be Webbers one day. Try to come up with an analog to Hubble huggers for Webb. Webb Wubblies? Okay, I don't know about that one. We'll have to think about that. We'll table it. So Scott, how am I doing? Do you got anything from Twitter for us, or let me look at the YouTube comments.
I'm looking around right now.
Okay.
I'm screen sharing an image of a solar eclipse caused by the moon it's a satellite looking down on the Earth.
Yeah.
A photograph of an eclipse as it crosses the surface of the Earth. So that's the shadow of the moon. And you can see a similar thing where there's the dark part in the middle, the umbra, and then the penumbra around it. So it's pretty cool.
Okay, so here's a comment from YouTube. I'll go ahead and put this up, and maybe somebody can comment on it. Kuna GQ from YouTube is going, looking at the picture posted on the NBC News website, which linked to this YouTube site, I can't figure out why the shadows don't seem to be in a consistent position with respect to the respective moons. The bottom left moon appears to be casting a shadow, as if the sun is off to the left in the photo, and the top right moon appears to be casting a shadow, as if the sun was above and to the right. What am I missing here? Was this some kind of combined time-lapse photo?
No. I think it would really help to look at the version of the image where everything is labeled, because I think what's going on is in an unlabeled image, it's hard to tell which shadow goes with which moon. But all the moons are casting shadows to the right.
Right. The vector is the same. Yeah.
The moons are also at different distances.
Yeah.
So the shadows are offset. But yeah, I think, Mike, you're right. You have to look at those labeled ones to connect which shadow goes with which moon. It is confusing.
The parallax
so
effect
the sun is over your left shoulder as you look at this.
Yeah.
Way off to your left shoulder.
It's a little confusing because Io is right over Callisto's shadow at some point.
Right, exactly.
And in fact, before our observations started, earlier on, Io's shadow was passed over Callisto's shadow. We couldn't observe during that time.
Oh, that's too bad.
So there's lots of funny little things. And my understanding also is that Io actually got eclipsed by Callisto, I believe, at some point. So Callisto's shadow passed over Io. That would have been cool to get, but again, we couldn't schedule that. We only have such a limited little slice of time.
I think we did good with our one orbit.
Yeah, it's great.
I think we did awesome with our one orbit.
Fun facts, yeah.
But yeah, you know, there's so many little things going on. It's so dynamic.
All right. Well, folks, I guess I'm just trying to. Jonathan Eisenhammer posted something. APOD. Is it an astronomy picture of the day? I didn't see that.
No, it's the same image that Carol put up there as far as showing the Umbra and Penumbra on there. From 1999. But yeah, I'm hoping it goes up tomorrow for APOD.
That would be awesome. Yes, that would be great. Okay, well, guys, I guess that's it for today. This week, I want to thank you, Zolt and Mike and Susanna for joining us. This has been a great hangout. Lots of fun stuff. Next week, our hangout will be it's another hangout in sort of celebration of our 25th anniversary of Hubble's launch, where we will be looking at a collection of pictures we've assembled. It's on our Hubble25th.org site. We'll be talking about 25 different images to commemorate different science, the different science missions and things that Hubble has done throughout its lifetime. So we hope you will join us then. That will be next week, Thursday at 3 o'clock. So I guess that's it, guys. Carol, Scott, anything?
Hey, thank you.
Been great.
All right.
That's good.
Okay, guys. Well, I want to thank you all for watching, and we'll hope to see you next week. And don't forget, video contest. We hope to see your Ode to Hubble videos soon. So start getting your creative juices going, and we hope to see your videos real quick. So that's it for this week. Thank you all for watching. And as always,
see you later, Hubblers.
Hubblers.
See you later, Hubblers.
Bye.
Keep looking up,
We get a
Hubblers.
T-shirt.
Keep looking up, Hubblers. I guess it happens every few decades or something like that. It was very rare event that we got here, and with us is the members of the Hubble Heritage Team, and we invite your questions and comments also. If you want to interact with us, we have you can comment on the Hubble Hangout event that we're on G+. You can also tweet using the Hubble Hangout hashtag, as well as using the Q&A app. That's actually the best way to interact because I'm monitoring that, and you can also leave comments on the YouTube page that we're broadcasting from. So, with joining me as she always does is Dr. Carol Christian. She's the HST outreach scientist, as well as the driver of the internet, Scott Lewis at Scientific Scott. Hi, Scott.
How's it going, Tony?
Really good, thanks. And thank you guys for joining me. And so today's panel we have Zolt LeVay. He's the guy who I think is one of the persons most prominent in the Hubble Heritage Team. Hi, Zolt. We also have Dr. Mike Wang. He's an astronomer at the University of California, Berkeley. Hi, Mike. And Susanna Duestra. She's an astronomer at the Institute. She's joining us also. Welcome, everybody.
Hello.
Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and I work at the Space Telescope Science Institute. And this week, we've got a really great hangout planned for you. As we usually do, this week we are taking a look at some of the, as many times, Hubble has been sort of identified as using and looking at far away distant objects. But this week we're highlighting some objects where we inside the solar system, a little bit closer to home. And this week, today, in fact, we have released some new images, new observations of Hubble's looking at Jupiter. And we have with us members of the Hubble Heritage team, as well as some astronomers who have also helped with these observations. But before I get started, I have a couple of announcements I want to make. This week on Monday, if you go to spacetoLescope.org, there is a video contest that just opened up called Ode to Hubble. And if you would like to celebrate Hubble's 25th anniversary, you are invited to make a video and submit it on YouTube, and then enter that into the contest itself. The link is on the web. I put it on the event page here. It's on the event as well as the event. Okay. And Zol, let me start with you. What have we got here? We've got some images and observations of Jupiter. So why don't you describe a little bit what we've got here?
Okay, so we were able to get one orbit with Hubble. We were privileged enough to get one orbit to look at a fairly rare event, the crossing of several moons across the face of Jupiter, several of Jupiter's moons across the face of Jupiter. If I could start by opening my screen, I can show you these images. And what we have here is two images of Jupiter. Can you all see that?
Yep,
yes.
You see it just fine.
So there are two images of Jupiter taken at different times, about roughly 40 minutes apart. So on the left, we see the disk of Jupiter with those bands of clouds, dark and light clouds. And then we see a number of dots on top of it. On the left, we see a kind of brown, on the left-hand panel, on the lower left, we see a brownish image, and that's the moon Callisto. And to the lower right of that is a black dot right on the edge of Jupiter, and that's a shadow of a
description of the YouTube video that we're broadcasting on. So we hope you will join. There are two categories: if you are under 25 and if you are over 25. Now, if you're under 25, that means that you don't know a world without the Hubble Space Telescope, and we're affectionately calling you the Hubble generation. For those of you over 25 years old, there's a separate category, and the prize is
and it comes with the Geritol backpack.
That's right, it comes with Geritol. But the prize is really cool. They are offering a piece of the solar array that actually was part of Hubble early on in its mission, and as well as a plaque and a variety of other things. So please check out the link below in the description, and we hope to see your video soon. Now, if you have any questions or issues like that, just by all means let us know, and we will help you and as much as we can in getting those videos submitted. So we look forward to seeing what you've got this week. So let's get to this hangout. This week we are talking about Hubble has observed Jupiter, and we've gotten some really great observations. In fact, there's a very somewhat rare conjunction that happens every
another moon, Europa, which we don't actually see in that image. Up towards the upper right, we see a yellowish moon, and that's Io, very interesting moon of Jupiter. And to its upper right, we see its shadow, fairly sharp and distinct shadow. And just below Io, we see another shadow, and that's actually the shadow of Callisto, which is way off to the lower left. So the Callisto's shadow is much farther away from Callisto than Io's shadow is away from it, and that's because Io is much closer to Jupiter. Also, you may notice that Callisto's shadow is much fuzzier, it's much less distinct, and that's also because Callisto is much farther from the planet than Io is. On the right, we have the same, basically the same view of Jupiter, but everything's moved. So the moons have all shifted because they're orbiting around Jupiter at a rather rapid clip. And so Io is now off, almost off the disk on the right-hand, upper right-hand side. And Europa, now we can see Europa itself just inside the edge at the lower left, and Europa's shadow is off to its upper right. and we still see Callisto moved over and Callisto's shadow. So those are the